Hey everyone, Mr. Smith here again. We're doing some more work with algebraic vectors today. Bryden wants to say hi. I'm going to show them your tooth, missing tooth. Tooth fairy came to our house a couple days ago. What does a tooth fairy give these days, Bryden?
Toonies and quarters.
How much?
Toonies and quarters.
You got a toonie, right? Yeah, that's the going rate, I guess, right? All right. What do you want to say to my students?
Have a good day.
That's nice. Okay, bud. We'll see ya. Bye. All right. So today we're taking our knowledge of algebraic vectors, doing a few more things with it, and maybe solving some problems we did with geometric vectors a little bit easier with algebraic vectors. So I say yesterday here, of course, could be the same day or a couple days previous, depending on when you're viewing this. But we learned about unit vectors I hat and j hat. We said they're the building blocks for any vector in R2. So any vector, say u, u1, u2, you can write it as a linear combination of I and j. So if you want to do these as a bit of a warm-up, you can, or if you just want to follow along with me, you can too. But the vector -4, 0, I'll show like an extra step here. You don't have to show this if you don't want. That's like -4 times the vector 1, 0. That's -4 times the vector I hat, unit vector I hat. Of course, you could go directly to writing these 2 I hat plus 5j hat. You can have decimals too, no problem. 1.4 I hat plus 0.5 times j hat. But the idea is that any vector in R2 can be written as a combination of I hat and j hat. And even A doesn't have, A has is like 0 times j hat. We don't need to write that in, but yeah, every single vector in R2 can be written in terms of I hat and j hat with an associated number with each of them. Like for -4, 0, it was -4 and 0 on I hat and j hat, and so on and so forth. So because of that, we say that I and j, they span R2, because any vector in R2, you can write them in terms of I and j. Every single vector can be created. They span R2. This doesn't always happen with any two vectors. For example, let's say I had a vector, I'll call it u, and I had another parallel vector, I'll call it v. By taking linear combinations of u and v, I can't get wherever I want. I can only kind of get in a straight line, right? Even if I take v going backwards. So the idea here is if you take one vector and you take scalar multiples of it, you can span a line. One vector spans a line, right? And just visualize that. Imagine vector u and just doing different scalar multiples of it. They would always just form a line. But what do two vectors span? Two vectors span. What do two vectors span? So we've seen that I hat and j hat span R2, but we've also seen that two vectors, if they're parallel, won't span R2. They might just span a line. So the idea is that any two vectors that aren't collinear will span R2. So if you guys just have a look at 1, 2, and 3, 1, obviously they're not scalar multiples. They're not collinear. So they're going to span R2. And that means any vector in R2 you can make as a linear combination of 1, 2, and 3, 1. So let's illustrate that. So we're going to show that, we're going to express -1, 8 as a linear combination of 1, 2, and 3, 1. And afterwards, we'll illustrate what we did with our sketch. Now, so obviously, it would be easiest to express -1, 8 as, -1 times I hat plus 8 times j hat. That's an easy way to write that in terms of two kind of building block vectors. But our goal here is to show that you can do that with any two vectors that aren't collinear or parallel. So what we're doing here is essentially this. We're trying to write minus 1, 8 as, I'll call it A. Some number A times 1, 2 plus some number B times 3, 1. So we're trying to find those values A and B. So if you look at the x coordinates, A times 1 plus 3 times B has to give me -1. So that's just looking at the x values, right? 1 times A plus 3 times B, it has to give me -1. And then whatever A and B are, looking at the y values, we know that 2A plus B has to give me 8. And many of you guys hopefully recognize that is a linear system in terms of A and B. 2 linear equations with 2 unknowns. And we can solve that using our skills from our grade 10 course. So whether you like elimination or substitution, it doesn't matter. I think I'll use substitution for this one, and then use elimination for the next one I have to do. You can pause the video and do this if you'd like, or follow with me. So I have 2 good choices for substitution. I can get the A in equation 1, which I'll do, but I also could have easily isolated the B in equation, or the A in equation 1. I could have easily gotten the B in equation 2. So A is -1 minus 3 times B. Whatever A is, A and B are related in that way. And I can sub this into my second equation. Getting 2 times -1 minus 3B plus B equals 8. So this is just solving linear systems. You guys did this in grade 10. Hopefully you did some prerequisite work and just tried and brushed up on those skills. But this is a skill we're all just expected to have in our math toolbox at this point. So -2 plus 6B plus B equals 8. Did I make a sign error there? I did. That should be, I was just kind of doing the mental math, working ahead, and I was getting fractions. And I definitely didn't design this to have that. Yeah, so -6B, and now this will work out. So we get -5B, 8 plus 2 is 10, and then we get that B is -2. And now that we've gotten B, we can sub that back into what we had rearranged for A. A is -1 minus 3 times B, but B is -2. That's -1 plus 6, so A is 5. And so what we have shown is that the vector -1, 8 is 5 times the vector 1, 2, minus 2 times the vector 3, 1. And this is self-checking. 5 minus 6 is -1. 10 minus 2 is 8. Everything checks out. And I could do this with any vector at all. We did it with -1, 8. But 10, 17, -25, -17. Any vector I can write as a combination of U and V by doing this, setting up an equation like so, and then solving the corresponding linear system. So let's visualize what that looks like. So here's 1, 2. I'm not going to use a ruler here, but so that was vector U. So 5 times 1, 2 goes out here, 4, 5. There's 5 times 1, 2. Now vector V was 3, 1. 3, 1, looking like so. That was vector V. And -2 times that will go back in the opposite way. So there's one of them backwards, and then another one. Gets me, I definitely feel like I did that. Yeah, I went down too far. So I wasn't finishing off where I should. Yeah, definitely went too far. And then down another 1 over 3 gets me here, right there. And this is my resulting vector, negative 1, 8. So just visually showing the work we did there, we expressed negative 1, 8 as a combination of u and v by setting up a linear system. And again, you can do that with any vector you want. So why don't you try it? Whoops. Put my face down there. So we'll stick with u and v being 1, 2, and 3, 1, but this would work with any non-collinear vectors, but we'll stick with those guys. Try 50, 40. We just did negative 1, 8, but can you set up a linear system, find coefficients a and b that create a linear combination? This one won't be practical to sketch, so we'll just do this one algebraically. If you'd like to pause the video and try that, you can unpause when you're ready, or you can follow along with me right now. So our goal is to write 50, 40 as some number times 1, 2, plus another number times 3, 1. I'm using a and b. You could be using x and y. It doesn't matter. So setting up that kind of like vector equation is going to give you two equations, two unknowns when you break it up into components. So for the x's, 1 times a plus 3 times b is going to equal 50 this time. And 2 times a plus b will equal 40 this time. I'm going to find a and b. This time, I'm going to use elimination. So I'm going to multiply the first equation by 2. This, and I'm multiplying everything by 2. So that's equation 1 multiplied by 2. That matches up the a values. Same equation, it's just scaled up. And now by doing this, I'll call this equation 3. Now I can subtract. If I do equation 3 minus equation 2, and you might have your own little way of staying organized and explaining what you're doing. So 2a minus 2a is 0. 6b minus b, that's 5b. And then 100 minus 40 is 60. And we've eliminated a variable. We can solve for b equals 12. And now I can sub back into either of my equations. I think that the first one looks pretty easy to work with. Sub in 1. A plus 3 times 12 equals 50. That's 36. And 50 minus 36, a equals 14. And so the vector 50, 40, we've shown we can write it as 14 times the vector 1, 2, plus 12 times the vector 3, 1. And then you can self-check this. 14 plus 36 is 50. 28 plus 12 equals 40. I know it works. So we've done it with two vectors. Hopefully you guys are convinced. 1, 2, and 3, 1 spans R2. Any vector we can write in terms of 1, 2, and 3, 1. Great. So the next thing we're going to do is show you guys how we can use algebraic vectors to solve problems that we classically did with geometric vectors, like a velocity problem with like winds and currents and whatnot. We're going to take geometric vectors and write them as an algebraic vector or in Cartesian form. I'm going to use trigonometry. So if you recall, we use components last unit. We could break any vector v up into, like, say, a horizontal and vertical component. Laid out on the Cartesian plane like that, take a position vector v. Its horizontal component would be v cos theta. And here, this is important. Theta is the angle with the positive x-axis, so standard position. And the y component would be v sine theta. So we can write any vector v as the magnitude of v cos theta, comma, magnitude of v sine theta. So we can take a geometric vector where we know the angle with the positive x-axis and turn it into a algebraic vector. And this is good because remember, algebraic vectors are easy to add, subtract, etc. Geometric vectors weren't. If you recall those like velocity problems, we had to, draw the diagram, interpret where angles are, use cosine law, sine law, sometimes the ambiguous case. So it was challenging. What's cool about this is, think about this vector v is obviously in quadrant 1, and the angles between 0 and 90, cosine and sine are positive. And so you're going to get positive x value, positive y value. But say if you had, so remember the cast rule, say you had a vector in this quadrant where only sine is positive. Sine is positive, you're going to get a positive y value. If cosine is negative here, you're going to get a negative x value, and you actually see that the position vector you get has all the right signs. It's in this quadrant where x is negative, y is positive. So as long as you have the angle from the positive x-axis, using this v cos theta, v sine theta will get you the perfect algebraic vector every time. So that's pretty cool. But the one tricky part is, sometimes when we're working with like a velocity problem, you might get the angle as a true bearing, from 90. So we'll have to convert that to an angle that's with the positive x-axis in order to make an algebraic vector. So let's just get some practice doing that and then solve a problem. So here we have a 200 Newton force acting at 20 degrees from the horizontal. So something like so, 200 Newtons. I guess I didn't really say right or left, but that's fine. We'll assume 20 with the horizontal. So I can write this force as an algebraic vector by doing 200, its magnitude, times the cosine of that angle, and then 200 times the sine of that angle. And I might actually just leave it there. Like you could get those decimals if you really wanted to, if that was like a final answer. But for doing a problem, you might want to leave it that way just to save yourself some work. But yeah, it's that easy. Let's take another one. 100 Newton force acting north 10 degrees west. So north 10 degrees west is this way, right? So that's 10 degrees, 100 newtons. To write this force as a Cartesian vector, remember, we need the angle from the positive x-axis, right? I don't know if that's going to be enough room. So that's not too hard to find here. If it's 10 degrees from north to the westerly direction, and it's 90 from kind of like east to north, right? This is 90. And this entire angle is just 100 degrees, right? So I can write this force as 100 times the cosine of 100, and then 100 times the sine of 100. Now this one, I actually might do the decimals for this one to show you that you get all the signs checked out. Do 100 cosine 100. Make sure you're in degree mode. You get negative 17.4 roughly. And 100 sine 100 is about 98.5. And again, what's really neat is that by making sure we have that angle correctly, we get a nice algebraic vector. It's in the right quadrant. X value is negative, y value is positive. And now we could, if we had other forces, like for example, if I wanted to add these two forces together, I don't need to make a crazy diagram. I can just add the x values, add the y values, right? It's so easy. So now that we've done a couple examples, let's try a problem that we would have had to work pretty hard at in our last unit. We would have to draw a diagram, figure out angles, use sine law, cosine law. Let's do this problem using Cartesian vectors. So a ship's course is set to travel 23 kilometers per hour on a heading of north 40 degrees east, but there's a current flowing at 8 kilometers per hour flowing north 20 degrees west. And so the course, they're not going to go in their heading direction. They're going to get blown off in some other direction. We're going to find that direction. So the ship's course, north 40 degrees east. So north 40 degrees east is like that. So 23 kilometers per hour, north 40 degrees east. So for us, that will mean that our angle theta is 50 degrees. So I can write this down here. I'll say V for the ship's velocity is going to be 23 times the cosine of 50. times 20, or not times, and then for its y value, 23 times the sine of 50 degrees. And I'll leave it like that. Let's do the current. Current's flowing 8 kilometers per hour north, 20 degrees west. So something like this. Not diagram, not to scale for sure. 20 degrees here. And so that means that our angle theta, we need to convert into an algebraic vector, would be 90 plus 20, so 110 degrees. So the current, we can write as an algebraic vector as 8 times the cosine of 110 and 8 times the sine of 110. Sorry, my kid's grandparents have just showed up. They're going to be visiting outside, so they're stomping around pretty happy. Okay, try not to get distracted here. Okay, let's use this to solve our problem. So let's determine the resultant velocity of the ship. So remember, I'll just use R for resultant, I guess. To get the resultant velocity of the ship, we take the velocity of the ship's heading, where it's trying to go, but then the current's blowing it off course, and we add these two things together. And again, last unit, we would have to draw those two, use trigonometry. You may have found it pretty challenging. Here, though, we have these as algebraic vectors. So I'm going to flip back here. So it's 23 cos 50, 23 sine 50, plus 8 cosine 110, 8 sine 110. And you guys could literally do that in one step on your calculator. Like, I'm going to show this step here, but I don't expect you guys really to need to do this if you want to go right to your answer. So we're going to do 23 cos 50 plus 8 cosine 110 and 23 sine 50 plus 8 sine 110. And let's go ahead and do that. 23 cos 50 plus 8 cosine 110. So for x component, I'll go to 2 decimal places, keep lots of accuracy here, 12.05. And then 23 sine 50 plus 8 sine 110, 25.14. And that's it. Now, that doesn't tell us the magnitude and direction, but that's easy to find with a position vector, right? So 12.05, 25.14. That is somewhere, it's like something like that, right? And what we need to find is this angle, called theta again. And we want to know the magnitude of this resultant too. Well, that's easy to find. We're just going to use Pythagorean theorem, right? Remember, to find the magnitude of a position vector, we just use Pythagorean theorem with the individual components. So 12.05 squared plus 25.14 squared. Let's just do that right now. 12.05 squared plus 25.14 squared. And oh shoot, I cleared that. 12.05 squared plus 25.14 squared. I got about 27.9. And that would be kilometers per hour. And for the direction, we can just use inverse tan, right? Because that's about 12.05 in the x direction, 25.14. And so the angle is the inverse tan of 25.14 over 12.05. Let's do that. I got about 64.4 degrees. And so we've got it. The resultant velocity of the ship is 27.9 kilometers per hour. So it got a bit of a boost from the current. Didn't change its direction though. Its direction is now from east 64.4 degrees north. Or if you prefer, if you did this on your own and found the angle from north, that's fine too. It would be north 25.6 degrees east, and both mean the same thing. So I showed a lot of steps here. Initially we had to do a bit of work figuring out the angle of this, like the standard angle from the positive x-axis. Once we did that, it was easy to write those vectors as Cartesian vectors. It was easy to add them. I showed a lot of steps. You could probably shave a step or two off that. And then it was pretty easy from there to get the magnitude direction. And in my opinion, that's a lot easier than drawing a diagram. Most importantly, is this method can be kind of automated and programmed so you can have a computer do it. And then you can imagine in real time, if you have the wind speeds being constantly changing and different speeds at different positions and different directions, and the airplane's velocity constantly changing, their bearing would constantly be changing too. And you could have a computer constantly updating these vectors in real time, add in hundreds and thousands of planes, and you kind of have like a system for tracking air traffic, right? So it's pretty cool. But I hope you guys agree. Algebraic vectors are making our lives so much easier, including problems we did last unit. Your practice is also from the same section as our last lesson, just some different questions to try. It was just way too much to try to squeeze into one lesson. So give those a go. As usual, please let me know if you need anything or need any help. Hope you guys stay well, and we'll see you.